We begin with a question that echoes through the halls of science and the landscapes of our imagination. Did Mars ever support life? When we look up at the night sky, we see our neighbour Mars as a steady reddish pinpoint of light. For centuries, it has been the subject of our myths, our stories of war, and our dreams of alien empires. But as we moved from telescopes to robotic explorers, the fictions of little green men gave way to a much more profound and realistic possibility. Today, Mars is a brutal, cold, and sterile-looking desert. Its atmosphere is thin, almost a vacuum composed mostly of carbon dioxide. It is blasted by radiation that would be lethal to most life as we know it, and its surface is a landscape of rust, iron oxide, and dust. It is by all appearances a dead world, but the central question is not about Mars today. It is about Mars yesterday. Our rovers, orbiters, and landers have sent back overwhelming evidence that this was not always the case. The photographs and data show us a planet that is scarred by the memory of water. We see vast dried-up river deltas, smooth stones tumbled by ancient streams, and canyon walls carved by catastrophic floods. Our robotic chemists have drilled into the rock and found clay minerals and sulfates minerals that on Earth only form in the presence of liquid water. The evidence points to a Mars that existed 3 or 4 billion years ago. This ancient Mars had a thicker atmosphere, it was warmer, and it had vast quantities of liquid water on its surface. It had rivers, it had lakes, and it may have had a shallow, salty ocean in its northern hemisphere. This is the crucial point. Billions of years ago, Mars looked remarkably similar to the Earth at the very same time, and it was during that exact same period on Earth that life first emerged from the primordial soup. The ingredients were all there. Mars had liquid water. It had energy sources like sunlight and the heat from volcanoes. It had the essential building blocks, the organic molecules rich in carbon, which we know are delivered all the time by comets and asteroids. Mars had the same starter kit that Earth did, so the question becomes inescapable. If Earth, with those ingredients, sparked into life, did Mars? This is where the investigation transforms from a simple geological survey into a deep philosophical quest. This search is not just about rocks and chemical signatures, it is a search for ourselves. It touches the very core of what it means to be human, challenging our most fundamental assumptions about our place in the cosmos. For all of our recorded history, humanity has operated under the assumption of its own uniqueness. We are, as far as we know, the only example of consciousness, the only species on the only planet to look back up at the stars and wonder what they are. We are the universe made self-aware. This knowledge creates a profound, almost terrifying sense of cosmic isolation. We are an audience of one watching a magnificent play. The question, are we alone, is not a trivial one. It is the heaviest question we can ask. Finding life on Mars, even if it is not intelligent life, even if it is just a microscopic fossil, a chemical residue, or a strand of alien DNA locked in ancient ice, would change the answer to that question forever. It would mean we are not alone. It would mean the silence of the universe has been broken, and we are not the only voice. This discovery would reframe our entire origin story. Earth would no longer be a singular divine miracle. Instead, it would simply be one of 2 neighbouring planets where biology took root. It would move the study of life from a history, the story of Earth, into a science, the comparative study of biologies. We would finally have a second data point. This is why the search is so compelling. It's not just about finding an alien, it's about finding context for ourselves. Furthermore, if Mars is a world where life did exist but failed, it serves as a chilling and powerful warning. If Mars once had a vibrant biosphere and is now a tomb, it means that habitability, a planet's ability to host life, is not a permanent condition. It is a fragile, fleeting state. What happened to Mars? Did it lose its magnetic field, allowing the solar wind to strip away its atmosphere and water? Did its core cool too quickly? Whatever befell Mars, it would force us to look at our own planet with a new sense of urgency and fragility. The Martian ghost story would become a cautionary tale for humanity's future. This leads us to the final and perhaps most mind-bending implication. If life did begin on Mars, what does that tell us about the rest of the universe? Think of it like a recipe. We know the ingredients for life, water, carbon-based molecules. Energy are extremely common. We see them in distant gas clouds and in the asteroids that rain down on our own solar system. This great unknown has always been the spark, the mysterious transition from non-living chemistry to living, reproducing biology. We have no idea how hard that step is. Is it a 1 in a trillion miracle that requires conditions so specific that it only happened once, here on Earth? Or is it an easy, almost automatic step? Is life a natural, inevitable consequence of planetary chemistry? Right now, we cannot answer that. We are trying to understand the rules of music, having only ever heard a single song, Earth life. If we find that life also started on Mars, a neighbouring planet with a slightly different set of conditions, it implies the recipe is easy. It means the spark is not a rare miracle. It means that if you mix the right ingredients and give them time, life happens. This would fundamentally change our expectations for the cosmos. In the last few decades, we have confirmed the existence of thousands of exoplanets orbiting other stars. We believe there are billions, perhaps hundreds of billions of planets in our galaxy alone. Many of these are in the habitable zone, the right distance from their star for liquid water to exist. If life can start on two separate planets in one small solar system, the odds for the rest of the universe become staggering. The discovery would flip a cosmic switch. The probability of life elsewhere would change from possible but unknown to highly probable and likely common. The universe would transform in our minds from a sterile, empty void into a cosmic garden, a living galaxy teeming with potential. We would no longer be the definition of life. We would be just one variation of it. This is the true scope of the question. We are not just digging in the red sand for microbes, we are searching for the answer to whether life is a rare accident or if the universe is fundamentally built to be alive. Rewinding time. Mars 3.5 to 3.8 billion years ago. To understand Mars, we must first forget the world we see today. The modern Mars is a frozen, dusty desert with an atmosphere so thin that liquid water boils away into space. But if we could travel in a time machine back about 3.5 to 3.8 billion years, we would not even recognize the planet. This ancient time in Martian history is called the Noachian period. During this era, Mars was a much more active and dynamic world. Giant volcanoes, including the ones that would one day build Olympus Mons, the largest volcano in the solar system, were erupting constantly. This acid volcanic activity pumped huge amounts of gas into the sky. These gases included water vapor, carbon dioxide, and sulfur compounds. All this gas created something Mars desperately lacks today, a thick atmosphere. This atmosphere, likely much richer in carbon dioxide than Earth's, acted like a planetary blanket. It trapped heat from the sun in what we call the greenhouse effect. This process kept the planet's surface significantly warmer than it is today. It was still probably a cold planet, but it was warm enough for a precious substance to exist in its liquid form, water. Even more importantly, evidence suggests that during this early period, just Mars had a global magnetic field. Just like Earth's magnetic field, this would have created but an invisible shield around the planet. This shield protected the new thick atmosphere from the solar wind, a constant stream of harsh particles flying from the sun. This protection was the key to keeping the planet wet. So the picture of ancient Mars is not a dead red world. It is a geologically active, cloudy and warmer world with a protective magnetic shield. It was a world that had all the right conditions to host a water cycle much like the one we have on Earth. A world of water. The single biggest difference between ancient Mars and modern Mars is water. Today, the only water we know of for certain is frozen solid at the poles or buried underground as permafrost. Back in the Noachian period, water flowed freely across the surface. This is not just a guess. The evidence is carved into the planet's face. When our orbiters and rovers look at the Martian surface, they are looking at a geological history book. These machines have shown us undeniable proof of a wet past. Evidence from the sky. Our orbiters, like the Mars Reconnaissance Orbiter, have mapped the entire planet in stunning detail. From high above, they see vast winding valleys that look identical to river systems on Earth. They have meandering patterns branching out into smaller streams called tributaries, just as the Nile or the Amazon does. Scientists have also identified what look like ancient shorelines tracing the edges of enormous long-gone lakes. In fact, many scientists believe the entire northern hemisphere of Mars, which is much lower and flatter than the south, may have once been the bottom of a shallow, massive ocean. Evidence on the ground, this is where the proof becomes undeniable. Our robotic explorers, the Mars rovers, have acted as geologists on the surface. The Curiosity rover exploring Gale Crater found rocks made of smooth, rounded pebbles. These pebbles were cemented together in a way that only happens at the bottom of a fast-moving river. They were tumbled and smoothed by flowing water just like stones in a creek on Earth. The Perseverance rover landed in Jezero Crater for one specific reason. From orbit, we could see it was a perfect fan-shaped river delta. A delta is a special landform created when a river flows into a large standing body of water, like a lake or an ocean. The river slows down and drops all the mud, sand and sediment it was carrying. Finding a delta is proof positive that a river and a lake existed in that spot for thousands, perhaps millions of years. Both rovers have also found hydrated minerals. These are types of clay and salts like gypsum that by their very chemical nature must form in the presence of liquid water. When you put all this evidence together, the picture is clear. Billions of years ago, Mars was a water world. It had rain clouds, rivers that flowed, lakes that you could stand next to, and possibly even a great northern ocean. Water is the key. Why do scientists get so excited about finding evidence of ancient water? It is because in our search for life beyond Earth, liquid water is the one thing we believe is absolutely essential. We follow a simple strategy: follow the water. This is because of what we call life as we know it. While we can imagine strange forms of life that might exist in ways we cannot predict, we only have one example of life to study: life on Earth. And every single living thing on our planet, from the smallest bacterium to the largest blue whale, depends on liquid water. Water is special. Scientists call it the universal solvent. This means that more substances can be dissolved in water than in any other common liquid. This ability is critical for life. Life is based on chemistry. To make life happen, you need complex molecules like proteins and DNA to meet, interact, and perform tasks. Water acts as the perfect liquid meeting place. It dissolves nutrients, chemicals, and salts, transporting them into and out of living cells. It is the soup in which the chemistry of life happens. Other liquids exist in the universe, such as liquid methane on Saturn's moon Titan. But methane is only liquid at extremely cold temperatures around -80 degrees Celsius or -290 degrees Fahrenheit. At these frigid temperatures, chemical reactions happen so slowly that it would be very difficult for complex life to ever get started. Water, on the other hand, is liquid at a much more energetic range of temperatures. It provides a stable, protected environment. A deep lake or ocean can also protect fragile emerging life from harmful ultraviolet radiation from the sun, which was especially strong on early Mars. Because of this, finding a place that had liquid water for a long period of time is like finding the perfect laboratory for life to begin. The important distinction: habitable does not mean inhabited. This brings us to the most important idea in the search for life on Mars. We have found overwhelming evidence that ancient Mars was habitable, but this does not mean it was inhabited. This is a critical difference. Habitable means all the right ingredients for life were present. Think of it like a kitchen. Ancient Mars had the flour chemical building blocks called organics, which we have found. It had the heat and energy source like the sun or chemical energy from volcanoes, and it had the mixing bowl liquid water. All the raw materials needed for life to start were there. The kitchen was open and ready. Inhabited means life actually started. It means the ingredients were baked into a cake. This is a much bigger step. We still do not fully understand how life started on Earth, so we do not know if it is an easy common event or an incredibly rare miracle. It is entirely possible that Mars was habitable for 1 billion years with beautiful rivers and lakes, but that life simply never began. Maybe the spark never happened. This is the entire point of our current missions. We have already proven that Mars was habitable. The rovers Curiosity and Perseverance are now looking for biosignatures. These are the signs that life was there, not just the ingredients. They are looking for preserved patterns in the rocks, specific types of complex organic molecules, or even microscopic fossils of ancient Martian microbes. This is why the Perseverance rover is collecting rock samples. The plan is for a future mission to pick up these samples and bring them back to Earth. Only in our most advanced labs on Earth can we finally answer the big question: was the habitable Mars also an inhabited Mars? To find these elusive signs of ancient life, we cannot go to Mars ourselves. Instead, we send incredibly sophisticated robotic explorers. These robots are our eyes, hands, and laboratories on the red planet. For the past 2 decades, a series of rovers have rolled across the Martian surface, but 2 stand out for their advanced capabilities: Curiosity and Perseverance. The Curiosity rover, which landed in Gale Crater in 2012, is essentially a mobile geologist. Its primary mission was not to find life itself, but to answer a fundamental question. Did Mars ever have the right environmental conditions to support small life forms called microbes? Its mission is one of assessing habitability. Curiosity is equipped with a powerful laser to vaporize tiny bits of rock and analyze their chemical makeup from a distance. It also has a drill to collect rock powder and deliver it to advanced laboratories hidden inside its belly. In its years of exploration, Curiosity hit the jackpot. It discovered that Gale Crater was once a massive, long-lived freshwater lake. It found the chemical building blocks of life, including complex organic molecules, the compounds based on carbon that are essential for life as we know it. Curiosity proved beyond a doubt that ancient Mars was habitable. This discovery set the stage for the next, more ambitious mission. If ancient Mars could have supported life, the next logical step is to search for direct evidence that it did. This is the job of the Perseverance rover, which landed in 2021. Percy, as it is nicknamed, is a dedicated astrobiologist. It is an upgraded version of Curiosity, carrying a new set of tools designed specifically to hunt for biosignatures, which are the telltale signs of past or present life. These signs could be fossilized microbial patterns in rock textures that microbes might have created, or specific clusters of organic chemicals that are difficult to produce without biology. Perseverance also has a groundbreaking new job. It is the first step in a Mars sample return campaign. While Percy is smart, the most powerful laboratories are still here on Earth. Perseverance is equipped with a complex system that drills small pristine cores of rock, each about the size of a piece of chalk, and seals them in super clean metal tubes. It then strategically drops these tubes on the Martian surface. The plan is for a future mission to land nearby, retrieve these carefully selected samples and launch them back to Earth for intense study by scientists in labs around the world. This is our best hope for definitively answering the big question. With such a critical mission, the landing site for Perseverance had to be perfect. After years of debate among thousands of scientists, NASA selected Jezero Crater. This 28-mile wide, 45-kilometer wide impact basin is considered the holy grail for Martian astrobiologists. Why Jezero? Because billions of years ago, this dry, dusty crater was a place of astonishing Earth-like beauty. It was a deep, calm lake fed by a winding river. Scientists know this with near certainty, because satellite images show the undeniable leftovers of this ancient water system. On the western edge of the crater, there is a clear inflow channel, where a river breached the crater rim. Even more importantly, where that river flowed into the standing water of the lake, it deposited a massive fan-shaped feature. This is a classic river delta. On Earth, deltas are teeming with life. The river carries nutrients from the land, the water provides the medium, and sunlight provides the energy. If life ever emerged on Mars, a location like the Jezero Delta would have been a prime habitat. It offered the three essential ingredients for life: liquid water, the necessary chemical elements, and a source of energy. The river that fed Lake Jezero didn't just carry water, it also acted as a conveyor belt, gathering rocks and minerals from a huge watershed outside the crater. This means that in one location, Perseverance can study a wide variety of rock types: volcanic rocks from the ancient highlands, carbonated minerals that may have formed along the lake's shoreline, and fine-grained mudstones from the deep lake bed. This geological diversity gives scientists the maximum number of chances to find a rock that recorded and preserved evidence of life. If life ever existed on Mars, a place that combined water chemicals and energy like Jezero is the single best place to look for its fossilized remains. The delta inside Jezero Crater is not just special because it was a likely habitat. It is special because it is the perfect environment for preservation. This is the key to the entire mission. Finding a place where life lived is only half the battle. We must find a place where its delicate signatures were protected from destruction for over 3.5 billion years. Here is how a delta works its magic. A river moves relatively quickly, carrying a heavy load of sediment, everything from large sand grains to microscopic particles of silt and clay, which are essentially mud. When this fast-moving river hits the still open water of a lake, it slows down dramatically. As it slows, it loses energy and can no longer hold on to the sediment it was carrying. The sediment begins to settle out. The heaviest particles, like sand, drop first right at the mouth of the river, but the lightest, finest particles, the silt and clay, are carried further out into the lake, where they hang suspended in the water before settling down in a slow, gentle rain onto the lake floor. This process is ideal for trapping and preserving any organic matter or delicate microbial structures in the water. Imagine a colony of microbes living on the lake bed, the remains of dead microbes floating in the water. They would be gently buried by this constant soft shower of fine mud. This mud blanket does two crucial things. First, it seals the organic material away from the harsh environment, protecting it from being destroyed by the chemical reactions, or in later eras by the intense ultraviolet radiation from the sun that bathes the Martian surface. Second, the clay minerals in the mud are known to be excellent at binding with and stabilizing organic molecules, locking them in place. Over billions of years, as more and more layers of sediment piled on top, the pressure mounted, and this ancient microbe-rich mud was slowly compressed and cemented into rock. The result is mudstone or shale, a rock that acts as a perfect time capsule. The fossils or chemical fingerprints of life are locked inside safe from the hostile surface. This is why Perseverance is drilling into these specific delta-front rocks. It is tapping into an ancient lakebed, accessing a geological vault that has kept its 3-billion-year-old secrets safe, just waiting for a robotic explorer to come and find them. This is a journey into the biggest question we can ask. The answer we find or don't find on Mars will echo back to Earth and change how we see ourselves forever. It's not just about biology, it's about philosophy. It's about our place in the cosmos. Let's imagine the first scenario. We find life. After decades of searching, a rover drills into the ice, pulls up a sample, and the microscope confirms it. Tiny wriggling organisms, bacteria maybe, or something we can't even categorize. The key question would be, is this life related to us? If a meteor struck Earth millions of years ago, it could have blasted Earth-based microbes all the way to Mars or vice versa. If we check its genetics and find it shares a common ancestor with us, that's amazing. It means life can survive space travel. But the truly universe-shattering discovery would be finding life that is not related to us. A second genesis. This would mean that in one single solar system, life started from non-living chemicals 2 separate times, completely independently. If that happened, it changes everything. Right now, we have only one example of life on Earth. This is a data point of 1. From a statistical point of view, that's useless. We have no idea if life is 1 in a trillion miracle or an inevitable chemical process. But if we find a second independent origin story right next door, it proves life is not a miracle. It proves that life is common. It would mean that the spark of life, the jump from simple chemicals like carbon and water to a living, reproducing cell, is not hard. It would mean that wherever you have the right ingredients, liquid water, an energy source, and basic organic molecules, life will almost certainly appear. Think about what that means when we look up at the night sky. We know there are billions of planets in our galaxy alone. We know many of them are in the habitable zone where liquid water could exist. If the spark of life is easy, then the universe must be absolutely teeming with simple life. It would mean the cosmos is a cosmic jungle full of microbes, alien algae, and simple creatures. The search for life on distant exoplanets would change from a question of if to a question of when and what kind. We would know deep in our bones that we are not alone. Now let's explore the second scenario, which is just as profound. We find nothing. This is the scenario of silence. We search for another 50 years. We send advanced robots that drill miles deep. We check ancient riverbeds, underground lakes, and volcanic vents. We find the ingredients in abundance. We find frozen water. We find complex carbon molecules. We find chemical energy. We confirm that ancient Mars was warm, wet, and had all the building blocks of life. It was a perfect kitchen, fully stocked with every ingredient needed to bake the cake of life. But after all that searching, we find nothing. No microbes, no fossils, no chemical traces of past biology. The kitchen is sterile, the ovens are equaled. This discovery would be haunting. It would suggest that having all the right ingredients is not enough. It would mean that the spark of life, the jump from non-living chemistry to the first living cell, is not easy. In fact, it must be an event so rare, so astronomically unlikely, that it happened on Earth but failed to happen on its nearly identical twin planet right next door. This would make life on Earth beyond precious. It would make us a miracle. It would strongly imply that we are the only life in our solar system. And if it's that hard to start, it might mean we are the only life in the entire galaxy. This rare Earth hypothesis would mean we are the sole consciousness that the universe has produced, floating in a vast, empty and silent ocean. The sky would still be full of planets, but they would just be beautiful, sterile rocks. The responsibility on our shoulders to protect this one-time only spark of consciousness would be immense. This brings us to a concept known as the Great Filter. This idea tries to answer a famous question: where is everybody? Our universe is over 13 billion years old. Our galaxy is huge. There has been more than enough time for other civilizations to evolve, develop technology, and spread across the stars. Yet when we listen with our radio telescopes, we hear nothing but cosmic static. The sky is silent. The Great Filter theory says that there is some step, some barrier on the long path from a dead planet to a spacefaring civilization that is almost impossible to pass. Life hits this filter and dies. Think of the path to civilization as a series of steps. The right planet forms with the right chemistry, like water. Simple single-celled life like bacteria emerges from non-living chemicals. That simple life evolves into complex multi-celled life like plants or animals. One of those animals evolves high intelligence and self-awareness like humans. That intelligent species develops technology like radio computers and rockets. that technological species must survive its own technology like nuclear weapons or climate change long enough to spread to other stars. The Great Filter is one of these steps. The terrifying question is, where is it? Is the filter behind us or is it in front of us? This is where our search on Mars provides the most important answer humanity may ever find. If we find life on Mars Scenario 1, especially life that started on its own, it means that step 2 on the list is easy. This is paradoxically the worst news we could ever receive. Why? Because if simple life is common but the galaxy is silent, it means the filter cannot be in our past. It must be in our future. It would mean that the hard part isn't starting life. It would mean that the filter is likely step 6 surviving our own technology. It would mean that almost every single civilization that reaches our stage of development inevitably destroys itself. Finding microbes on Mars would be a great warning. It would mean that we are rapidly approaching the same filter that has killed off everyone else. But if we find nothing on Mars Scenario 2, if we find that sterile kitchen, it is the most hopeful news we could imagine. It's a lonely discovery but a triumphant one. It would mean that step 2, the spark of life, is the Great Filter. It would mean that starting life is the miracle. It would mean that the hardest part is behind us. We passed the impossible test just by existing. This would mean the galaxy is silent, not because everyone is dead, but because no one else is out there. We are the first, we are the only ones, or at least the first in a very, very long time. The universe would be empty, dark, and quiet waiting for us. It would mean the future is completely open, and the only thing stopping us from reaching the stars is ourselves. The story of Perseverance's journey in Jezero Crater has reached a critical and exciting chapter. The rover's focus is now on a location nicknamed Bright Angel, and the findings here are not a single simple clue, but a sophisticated collection of evidence. This discovery is a textbook example of modern astrobiology, where scientists look for a package of clues that, when found together, tell a story that no single clue could tell on its own. The heart of the story. A focused investigation. The specific discovery at Bright Angel is the main event. Perseverance didn't just find one interesting thing, it found several different important clues all clustered together in the same small patch of rock. Imagine finding a single brick. That's interesting. Now imagine finding a brick next to a piece of a window, next to a door hinge, all buried in the same spot. You haven't found a house, but you have found a compelling package of evidence that a house once stood there. This is what Perseverance found at Bright Angel. It used its robotic arm to press its most advanced instruments against a specific patch of light-toned rock. In that single spot, it found a convergence of specific physical structures in the rock, specific organic molecules, the building blocks of life, specific minerals that are directly linked to water and on Earth to life. This discovery is about the combination of these clues, which makes the finding much more powerful and harder to dismiss as a random geological coincidence. The evidence package, not one clue but many. To understand the excitement, we must appreciate this idea of an evidence package. A single piece of evidence can often be explained in multiple ways. For example, organic molecules can be created by non-living processes like volcanic activity, or even delivered by meteorites. But what if you find those organic molecules inside a rock structure that could only have been formed by water and right next to minerals that on Earth are produced by living organisms? This is the evidence package. It's the convergence of all these features in one place, and it suggests that all these clues are related and were likely formed at the same time by the same set of environmental conditions. The Bright Angel package is so compelling because it contains all the key ingredients scientists look for when searching for a habitable environment. The clues in detail. Let's break down the 3 main parts of this evidence package that Perseverance identified. 1. Leopard spot structure, the physical clue. The first clue is something the rover's cameras could see. Scientists noted small circular and often concentric patterns embedded in the rock, which they nicknamed leopard spots. What they are. These spots are not just surface stains, they appear to be physical structures known as concretions or spherules. How they form on our Earth. These structures form when water-rich and dissolved minerals flows through a porous rock. As the water chemistry changes, those minerals start to precipitate or come out of the water. They build up layer by layer around a central point like a tiny grain of sand. Why they matter? These leopard spur are a clear physical fossil of water interacting with the rock. They prove that groundwater was present, flowing and chemically active for a long enough time to create these distinct shapes. This immediately makes them a prime target for a closer chemical look. 2. Organic matter. The chemical clue. This is perhaps the most exciting part of the package. Using the Sherlock instrument, which shines a laser on the rock, Perseverance detected the presence of organic molecules. What this means, organic, simply means the molecules are complex and built around atoms of carbon. Carbon is the backbone of all life as we know it, forming everything from proteins and DNA to the membranes of cells. What this does not mean. It is crucial to be clear this is not proof of life. Organic molecules can be created by many non-living processes. Why they matter? Finding these molecules is a critical first step. It confirms that the basic building blocks of life were present in this location. The kitchen of Mars had the necessary ingredients. The truly important part is where they were found locked inside these watery sedimentary rocks. Key minerals, the environmental clue. This is where the chemical story gets even more specific. The rover's instruments identified two very special categories of minerals in the exact same place as the organics. Phosphates like vivianite. Phosphate is a molecule containing phosphorus and it is non-negotiable for life. It forms the backbone of our DNA and is the key to how our cells store and use energy in a molecule called ATE. The rover found that this rock is loaded with phosphates. Evidence points to a specific iron phosphate mineral like vivianite. On Earth, vivianite often forms in oxygen-poor waterlogged environments that are rich in decaying organic matter. It's a sign of a very specific, promising environment. Sulfides like greigite. The instruments also detected iron sulfide minerals such as greigite. Like vivianite, greigite tells a story. It forms in watery environments that are reducing the opposite of oxygen-rich. On Earth, greigite is often associated with microbial activity. Some bacteria help produce it and others can use it as a source of energy. The power of co-registered data. This final point is what ties the entire evidence package together and makes it so scientifically strong. The discovery is powerful because of co-registered data. This is a technical term that simply means the rover's different instruments all analysed the exact same microscopic spot on the rock and confirmed each other's findings. This is how the instrument team worked together. Mascom's the eyes. This is the rover's main camera. It acted as the scout taking the high-resolution photos that allowed scientists to see the leopard spots and say, "That looks interesting, we should analyse it." Pixel the element. Mapper. The rover then placed its robotic arm against the rock. The Pixel instrument used a tiny, powerful X-ray beam to map the chemical elements present. Pixel is what said, "This tiny spot right here is extremely rich in phosphorus, iron and sulfur." Sherlock. The molecule detective. Working right next to Pixel, the Sherlock instrument then analysed the very same spot. Sherlock uses an ultraviolet laser to identify the specific molecules and minerals. This co-registration is the key. Pixel said, "Here are the elements." Sherlock then confirmed, "I can see how those elements are bound together. That phosphorus and iron are in the form of the mineral vivianite. That iron and sulfur are in the form of greigite. And look, I also detect complex organic molecules in the very same spot." This teamwork proves that the organics, the life-critical phosphates, and the energy-rich sulfides are not just random separate discoveries. They are all physically intertwined, existing together in a structure that was itself formed by water. This is the strongest evidence package yet that Bright Angel was once part of a complex, chemically rich and persistent aquatic environment, exactly the kind of place that could have supported life. In the search for life beyond Earth, the single most important rule is caution. Science is not a race to be first, it is a methodical process to be right. When scientists announce a discovery, especially one as profound as finding extraterrestrial life, they are putting their own reputations and the reputation of their entire field on the line. A claim that is later proven wrong can set back research for decades, waste billions of dollars, and destroy public trust. This is why the language of science often sounds so hesitant. You will rarely hear a scientist on the front lines of discovery say, "We have proven this." Instead, you will hear them say the data is consistent with, or "this suggests." This is not weakness, it is intellectual honesty. It is an acknowledgement that we are seeing only one piece of a giant complex puzzle. They must always leave open the possibility that a new piece of information could change the entire picture. This careful, skeptical approach is the core of the scientific method. Before a scientist can claim a biotic origin, meaning it came from life, they must first do everything in their power to prove an abiotic origin, meaning it came from non-living processes. This responsibility is called the burden of proof. In this specific field, the default assumption, the null hypothesis, is that it's not life. The scientist's job is to challenge that assumption, to try and fail to explain what they see using normal geology and chemistry. Only after every non-living explanation has been ruled out can they begin to whisper that the answer might be biology. Nature's deceptions. When geology fakes life. The greatest challenge in the search for life is that our planet's own non-living processes are experts at faking it. The Earth itself, through simple geology and chemistry, can create structures, minerals, and even complex molecules that look tantalizingly like the products of a living, breathing world. These false positives, or abiotic mimics, are the biggest hurdles astrobiologists face, faking structures. When we look for ancient life, we often look for fossils. For tiny life, like bacteria, we look for microfossils, tiny cell-shaped blobs, spheres, or long filaments, threads preserved in rock. The problem is that minerals, when they crystallize out of a chemical soup, can form these exact same shapes. Small spherical blobs of the mineral hematite can look identical to fossilized cells. Deposits of clay can form tiny branching filaments that are indistinguishable from fossilized bacteria. These pseudofossils are not alive and never were. They are simply the result of minerals settling out of water or forming under heat and pressure in ways that by pure chance mimic biological forms. Without a clear chemical signature inside the structure, a suspicious shape is just a suspicious shape. Faking molecules. This is perhaps the most difficult area of all. We are taught that organic molecules are the building blocks of life. This is true, but the word organic in chemistry simply means the molecule is based on a chain of carbon atoms. Life is carbon-based, but not everything that is carbon-based comes from life. Space itself is full of complex organic molecules. Floating in giant interstellar clouds and packed inside meteorites, we find amino acids, the building blocks of proteins and complex rings of carbon called polycyclic aromatic hydrocarbons, or PAHs. These were all formed by simple non-living chemistry where radiation and cold temperatures fused simpler atoms together over millions of years. On a planet, this is even more common. The most famous example is methane, a simple organic molecule made of 1 carbon and 4 hydrogen atoms. On Earth, much of our methane is biogenic. It's produced by microbes in swamps or by cows. But methane can also be abiogenic, a geological process called serpentinization, which happens when certain volcanic rocks react with warm water, produces huge amounts of hydrogen and methane. There is no life involved at all. So when our rovers detect a puff of methane on Mars, we cannot jump for joy. We must first ask, is this methane from microbes, or is it just the red planet's rocks reacting with underground water, faking with heat and water? Two geological processes are particularly good at creating these false signs of life: diagenesis and hydrothermal systems. Diagenesis is the name for all the changes that happen to sediment as it is slowly buried and turned into rock. As layers of mud and sand are piled on top, the pressure and temperature increase. This cooking process, unfolding over millions of years, can warp and destroy real fossils, but it can also take scattered, simple bits of non-living carbon and cook them into complex tar-like substances, kerogen, that look very much like the decayed residue of ancient life. Hydrothermal systems are even more deceptive. These are deep-sea vents, or black smokers, where superheated mineral-rich water bursts from the planet's crust into the cold ocean. These vents are chemical factories. As the hot acidic water mixes with the cold alkaline ocean, minerals instantly drop out of the solution building, towering chimneys full of tiny complex pores. These pores can look like a primitive cellular structure. Furthermore, the unique chemistry inside these vents, a mix of hydrogen, carbon dioxide, and mineral catalysts, can naturally synthesize complex organic molecules from scratch. These environments are in effect creating both the look of life structures and the food of life organics without any biology required. Space itself is full of complex organic molecules. Floating in giant interstellar clouds and packed inside meteorites, we find amino acids, the building blocks of proteins, and complex rings of carbon called polycyclic aromatic hydrocarbons, or PAHs. These were all formed by simple, non-living chemistry, where radiation and cold temperatures fused simpler atoms together over millions of years. On a planet, this is even more common. The most famous example is methane, a simple organic molecule made of 1 carbon and 4 hydrogen atoms. On Earth, much of our methane is biogenic. It's produced by microbes in swamps or by cows. But methane can also be abiogenic, a geological process called serpentinization, which happens when certain volcanic rocks react with warm water, produces huge amounts of hydrogen and methane. There is no life involved at all. So when our rovers detect a puff of methane on Mars, we cannot jump for joy. We must first ask, is this methane from microbes, or is it just the red planet's rocks reacting with underground water, faking with heat and water? Two geological processes are particularly good at creating these false signs of life: diagenesis and hydrothermal systems. Diagenesis is the name for all the changes that happen to sediment as it is slowly buried and turned into rock. As layers of mud and sand are piled on top, the pressure and temperature increase. This cooking process, unfolding over millions of years, can warp and destroy real fossils. But it can also take scattered, simple bits of non-living carbon and cook them into complex tar-like substances, kerogen, that look very much like the decayed residue of ancient life. Hydrothermal systems are even more deceptive. These are deep-sea vents or black smokers where superheated mineral-rich water bursts from the planet's crust into the cold ocean. These vents are chemical factories. As the hot acidic water mixes with the cold alkaline ocean minerals, instantly drop out of the solution building bizarre towering chimneys full of tiny complex pores. These pores can look like a primitive cellular structure. Furthermore, the unique chemistry inside these vents, a mix of hydrogen, carbon dioxide and mineral catalysts, can naturally synthesize complex organic molecules from scratch. These environments are in effect creating both the look of life structures and the food of life organics without any biology required. This is not proof yet. Because of all these geological fakes, no single discovery can ever be the final proof. Finding methane is not proof, finding a cell-shaped object is not proof, finding amino acids is not proof. Each of these is just a line of evidence. Proof only comes when multiple independent lines of evidence all point to the same conclusion and only that conclusion. To claim they have found life, a science team must present a comprehensive case. They must show that they found a signal, and then they must meticulously prove that no known non-living process could have made it. They must demonstrate that diagenesis could not have created that structure. They must prove that a hydrothermal system could not have produced that specific mix of molecules. They must show that the signal is not just contamination from Earth that they accidentally brought with them. This is why science is slow. It is a painstaking process of elimination. Every time a discovery is announced, like the potential signal of phosphine gas in the clouds of Venus, or the organic molecules found by the Curiosity rover on Mars, it is just the beginning of the story, not the end. It is an exciting clue that sends scientists back to the lab, tasking them with a new, harder job: try to prove that this isn't life. Only when they have tried everything and failed can they finally turn to the world and say that they have found something truly extraordinary. When we look for signs of past life on Mars, we are essentially acting as detectives, piecing together tiny fragmented clues left over from billions of years ago. To understand the story these clues tell, we have to look deeper at the molecules, the energy sources, and the physical structures left behind in the rock record. The first and most famous clue is the presence of organic molecules. This term is often misunderstood. In chemistry, organic does not automatically mean life. It simply means the molecule's structure is based on atoms of carbon, often bonded with hydrogen and other elements. While carbon is the essential backbone of all life as we know it, forming the basis for proteins, DNA and fats, it can also be created by many non-living or abiotic processes. So when our rovers find organic molecules trapped in ancient Martian mudstone, we must first ask where they could have come from. There are several non-biological possibilities. Mars is constantly bombarded by meteorites and interplanetary dust, many of which are rich in organic compounds formed in deep space. These molecules rain down on the surface and mix with the soil. Another source is chemical reactions driven by energy. The thin Martian atmosphere allows high-energy ultraviolet radiation from the sun to strike the surface. This energy can break down simple molecules like carbon dioxide and water and cause them to recombine into more complex organic compounds. Furthermore, ancient volcanic activity and hydrothermal systems where hot mineral-rich water circulates beneath the surface are powerful factories for creating organic molecules from simple ingredients, no life required. What makes the organics we have found so noteworthy is their complexity and their preservation. Finding simple methane is one thing, but finding complex ring-shaped molecules known as aromatic compounds or long chains of carbon is more intriguing. Life is a process of building. Takes simple molecules and constructs large, complex and specific structures. Finding these complex molecules suggests a more interesting chemical environment, and the fact they are preserved at all is amazing. The Martian surface is incredibly harsh with radiation and oxidizing chemicals that should destroy organics over long timescales. Finding them preserved in mudstone from an ancient lake suggests they were buried and protected quickly. However, to truly say this is life, we need to find the smoking gun fingerprints, which are clues our current rovers are not equipped to check. The first is chirality or handedness. Many important biological molecules like amino acids can exist in two forms that are mirror images of each other, just like your left and right hands. They are chemically identical but structurally opposite. Non-living chemistry produces these molecules in a roughly 50-50 mix of left-handed and right-handed versions. Life on Earth, however, shows a dramatic preference. It uses almost exclusively left-handed amino acids and right-handed sugars. If we were to find a sample on Mars with a strong preference for one hand over the other, it would be an incredibly powerful sign of a biological process. The other key fingerprint is isotope ratios. Carbon atoms come in different weights or isotopes, such as the lighter carbon-12 and the heavier carbon-13. Life is metabolically lazy and finds it easier to process the lighter carbon-12. As a result, organic matter from living things on Earth is measurably lighter. It has more carbon-12 than the non-living carbon in the environment. Finding a similar isotopic imbalance in Martian organics would be another profound clue. Of course, molecules alone are not enough. Life doesn't just need building blocks, it needs energy, it needs a food source to power its metabolism. This is where redox chemistry comes in. Life at its core is a tiny battery. It survives by harvesting energy from chemical imbalances in its environment. It does this by moving electrons from one molecule, an electron donor, to another, an electron acceptor. This flow of electrons is redox, short for reduction oxidation, and it is the food that powers a cell. On Earth, we get energy from eating donating electrons and breathing oxygen, accepting electrons, but on ancient Mars, life would have used simpler means. It would not have relied on sunlight for photosynthesis, but on the chemical energy stored in rocks. We call these organisms chemolitho-autotrophs, which breaks down to chemical chemo, rock, litho-self, autofeeders, trophs. They are rock eaters. They might eat hydrogen gas and breathe sulfate, or eat iron and breathe nitrate. This is why finding specific minerals like greigite and iron sulfide, and vivianite and iron phosphate is so electrifying. These minerals are not just rocks, they are fossilized records of a specific chemical environment. They only form in water that is reducing, meaning it is low in oxygen and rich in molecules that have electrons to give away. Greigite's presence points to an environment rich in iron and sulfur prime fuel for sulfur-metabolizing microbes. Vivianite is even more exciting. It locks up phosphate, which is the P in ATP adenosine triphosphate, the universal energy-carrying molecule used by all life on Earth. Finding these minerals tells us that the ancient lake environment was not just wet, but was a persistent, stable, low-oxygen, energy-rich environment that had both the food iron and the essential structural ingredients phosphate for a rock-eating microbial community to thrive. Finally, we look at the physical rock structures or textures, when the organisms themselves have long since decayed, and even their complex organic molecules have broken down. The large-scale shapes they built or influenced might be the only evidence left. It's like finding the footprint of a dinosaur even when the bone is gone. The importance of texture is about context. For example, finding thin laminations, paper-thin layers in the rock tells us the environment was extremely calm. This wasn't a raging river. It was likely a deep, still lake where fine sediment and perhaps mats of microbes could settle out slowly and build up layer by layer undisturbed. Even more compelling are concentric patterns or other organized non-random shapes. Geology can be random. It can create cracks in mud or jumbled piles of rock. But life is organized. It grows, it builds. Concentric patterns suggest growth outward from a central point or a collective response to the environment. On Earth, we see this in stromatolites. These are layered dome-like structures built by microbial mats in shallow water. The microbes on top grow toward the sun, trapping a layer of sediment. The next generation then grows up through that sediment, forming a new layer. Over thousands of years, this creates a large, distinctive layered rock that is undeniably the product of life. Finding a similar organized, repeating non-random structure on Mars would be a top-tier discovery. The real power, however, comes from combining all three clues. A strange organic molecule found alone could be from a meteorite. A weird chemical like greigite found alone just tells you about geology. A strange concentric shape found alone could be a bizarre crystal or weathering pattern. But imagine we find a concentric layered structure, and when we analyse its chemistry we find that the edges of the rings are rich in specific organic molecules like a bathtub ring left by the colony, while the core is uniquely enriched in phosphates, perhaps the fossilised remains of the cells themselves. This is when the case for life becomes almost undeniable. It is this combination, the right shape with the right chemicals in the right energetic environment, that moves the evidence from suggestive to conclusive. We have followed the clues across the red planet. We've seen the ancient dried-up riverbeds and the vast salty plains of vanished oceans. We've sniffed the air and found methane, a gas that on our own world is overwhelmingly produced by living things. We've drilled into the mudstone of ancient lakes and found the complex organic molecules that form the very building blocks of life itself. The evidence is tantalizing. It points, it suggests, it whispers, but it does not and cannot declare. We have now arrived at the most difficult part of our journey, the great, frustrating and absolutely necessary barrier known as the wall of certainty. This is the point where excitement must yield to extreme caution. Finding life on another planet would be, without any exaggeration, the single most profound and transformative discovery in human history. It would rewrite our textbooks, reframe our philosophies, and forever alter our perception of our place in the cosmos. And precisely because the stakes are so high, the standard for proof must be astronomically higher. In science, and especially in the search for life, the guiding principle is a famous phrase: extraordinary claims require extraordinary evidence. Claiming to have found a new type of rock formation is an ordinary claim. Claiming to have found the first example of biology beyond Earth is the most extraordinary claim we can possibly make. To get this wrong, to announce life and be mistaken, would be a scientific disaster. It would not only damage public trust, but could also send thousands of scientists down the wrong path for decades. This is why the astrobiological community is so careful, so methodical, and to an excited public so frustratingly slow. They are not just trying to be right, they are trying to be impossible to be wrong. To understand this deep-seated caution, we must look at a ghost that haunts every laboratory examining material from Mars. It's the ghost of a meteorite known as AL-84001. Back in 1996, the world was electrified by an announcement. A team of scientists analysing a potato-sized meteorite that had been blasted off Mars millions of years ago and had landed in the Allen Hills of Antarctica claimed they had found signs of fossilised life. The evidence looked compelling. Inside the rock, they presented images from powerful electron microscopes showing tiny segmented worm-like shapes. They looked for all the world like fossilised bacteria. But that wasn't all. They also found specific types of organic molecules known as polycyclic aromatic hydrocarbons, or PAHs, concentrated near these fossils, and then they found tiny crystals of a mineral called magnetite identical in shape to those produced by certain bacteria on Earth. It was a three-punch combination: a fossil-like shape, an organic food source, and a biological-looking byproduct. The evidence was so strong that the President of the United States, Bill Clinton, made a national address about the potential discovery. And then the rest of the scientific community got to work. Remember, extraordinary claims. Over the next several years, that extraordinary evidence was meticulously taken apart piece by piece. Other scientists replicating the work found that the worm-like nanofossils could be simple non-living mineral formations created by geological processes like hot water flowing through the rock. Those organic molecules, the PAHs. It turned out they are common in space and can be created by many non-biological processes. Worse, they are also a common contaminant from Earth. The meteorite had sat in the Antarctic ice for thousands of years, and its handling in labs could have introduced earthly organics. The same was true for the magnetite crystals. Scientists proved they too could form under high heat and pressure, such as the impact that blasted the rock off Mars. There was no smoking gun. Every single piece of evidence for life in AL-84001 had a plausible, if not probable, non-biological explanation. The ghost of AL-84001 is not a failure. It is a lesson. It is the single greatest cautionary tale in modern science. It taught us that looks like life is not good enough. This brings us to the immense burden of proof. When scientists on Earth find a complex organic molecule, their first assumption is that it's biological, a piece of decayed plant, a microbe, or industrial pollution. When a rover on Mars finds a complex organic molecule, the assumption must be the complete opposite. The default position always is that the signal is geological. The burden of proof is not on the skeptic to prove its geology, the burden of proof is on the scientist to disprove every single possible geological explanation. This is an almost impossible task. Let's take the methane plumes. Yes, it could be microbes, but it could also be a purely geological process called serpentinization, where deep groundwater interacts with certain minerals like olivine and releases methane as a byproduct, no life required. To prove it's life, scientists would have to prove it isn't serpentinization. But how can you do that from millions of miles away without knowing what's happening 5 miles beneath the rover's wheels? This is where we hit our final practical limitation, our robots. The rovers on Mars, like Curiosity and Perseverance, are the most complex exploration vehicles ever built. They are robotic geologists that are scientific marvels, but for all their sophistication, they are still just robotic geologists. They carry instruments, not a full laboratory. The tools on the rovers are excellent for screening. They can use a laser to vaporize a bit of rock and read its basic chemical composition. They can drill a sample, crush it, and bake it in a tiny oven, like the SAM instrument on Curiosity, to see what gases and organic molecules are released. This is how we found the thiophenes and other complex organics. But these instruments have limits. They can tell us, yes, there is a complex organic molecule here. They cannot tell us how it was made. They cannot show us a picture of the microbe that made it. They don't have powerful enough microscopes to see a living cell or a definitive microfossil. They can't sequence DNA or analyze the intricate handedness, a property called chirality of molecules, which is one of the most reliable signs of life as we know it. Think of the rovers as the advanced scouts. Their job is to find the X on the treasure map. They can find the most promising, biologically interesting samples and say, this spot is special, this is the one. But they cannot by themselves open the treasure chest. To do that, we must overcome this final wall. The only way to get the extraordinary evidence required is to bring those samples back to Earth. This is the entire goal of the Mars Sample Return mission. The tubes of rock and soil that the Perseverance rover is currently drilling and sealing are not for its own analysis. They are a message in a bottle left on the Martian surface waiting for a future mission to pick them up and launch them home. Only here in our massive, sophisticated labs on Earth can we truly put them to the test. Only here can we use building-sized instruments and every analytical technique we have to prove beyond a shadow of a doubt that every single non-biological explanation is impossible. Until that day, Mars will continue to hold its secrets, whispering hints of life, but forcing us to wait for the proof. For all the incredible work our robotic explorers have done, they have always been limited by 2 fundamental things: the power they can carry and the instruments they can fit. A rover like Perseverance is a marvel of engineering a mobile geological laboratory. But it is a mobile lab designed to be light enough to fly millions of miles and to survive on its own. The instruments it carries are miniaturized, simplified versions of their full-size counterparts back on Earth. They are brilliant for in-the-field analysis, for identifying promising locations and finding hints of past environments, but they cannot provide the final undeniable proof that life once existed. Answering a question of that magnitude, a question that would change our understanding of the universe, requires a level of evidence so precise and so robust that it can only be achieved in one place, a laboratory on Earth. That is why sample return is the ultimate and necessary goal of our search. It represents the transition from exploration to definitive science. It is the moment we stop asking, where should we look, and finally begin to analyze with our full power what we have found. The unmatched power of Earth's laboratories. When we bring a piece of Mars back home, we are not just bringing it to one instrument. We are bringing it to all of our instruments. We unlock the full potential of decades of scientific advancement. A lab on Earth is not limited by a 20-pound weight restriction or the power produced by a small solar panel. A single-purpose instrument on Earth can be the size of a car or even an entire room, drawing massive amounts of power to perform analyses at a precision unthinkable on another world. Furthermore, these samples can be studied by our best and brightest minds. They can be tested, retested, and then tested again with new techniques we have not even invented yet. A sample return today will still be providing new discoveries 50 years from now. This is the true power of sample return, unleashing the full capability of human science on the most important questions we can ask. High-precision isotope analysis. One of the most powerful tools we have for finding the fingerprints of life is the study of isotopes. Isotopes are simply different weights of the same element. For example, carbon, the basis of all known life, exists as the common carbon-12 and the slightly heavier carbon-13. In a non-living geological system, these 2 types of carbon would be distributed in a predictable random-looking ratio, but life is different. Life is, in a chemical sense, lazy. It prefers to use the lighter, more energy-efficient carbon-12. Over long periods, a community of microbes will preferentially eat and process the lighter carbon, leaving a distinct imbalance in the rock record. They create a concentration of light carbon that geology alone struggles to explain. A rover on Mars might be able to detect this imbalance, but it cannot measure it with enough precision to rule out all non-biological explanations. On Earth, we use massive room-sized instruments called mass spectrometers. These machines can take a tiny pinch of powdered Martian rock and count the atoms, providing a ratio so precise down to parts per billion that it becomes a smoking gun. A strong light carbon signature confirmed in a controlled Earth lab would be one of the most compelling pieces of evidence for ancient life imaginable. Checking for chirality-handedness. This concept is perhaps the most profound and specific sign of life we know. Many of the complex molecules that life uses, such as amino acids, the building blocks of proteins and sugars, are chiral. This means they can exist in two forms that are mirror images of each other, just like your left and right hands. If you create these molecules in a lab with non-living chemistry, you will always get a perfect 50-50 mixture of the left-handed and right-handed versions. It is a random outcome, but life is not random, it is specific. All known life on Earth, for reasons we still do not fully understand, is built almost exclusively from left-handed amino acids and right-handed sugars. This uniformity is a universal signature of biology. If we brought a sample back from Mars and discovered a collection of amino acids that were, for example, 90% left-handed, it would be an explosive, world-changing discovery. It would be almost impossible to explain through normal geology. This is not a test a rover can do. It requires complex, delicate procedures to extract organic molecules and analyze their three-dimensional shape, a process that requires a full-scale, sophisticated organic chemistry lab. Nanoresolution microscopy. When we search for ancient Martian life, we are likely searching for the fossilized remains of single-celled organisms. We are looking for microfossils. The key word, however, is micro. A rover's camera, even its close-up microscope, is like a powerful magnifying glass. It can see the texture of a rock and perhaps identify structures that look promising. But to prove that a tiny shape is a fossilized cell and not just a strangely shaped crystal, we need to see its structure. We need to see the remnants of a cell wall or a specific shape that could only be formed by a living thing. This requires a resolution at the nanoscale or billionths of a meter. On Earth, we use scanning electron microscopes or transmission electron microscopes. These are huge, complex devices that use beams of electrons instead of light to see features smaller than a virus. With this technology, we could take a single grain of sand from an ancient Martian lake bed and look for the unmistakable, ultra-fine detailed physical evidence of a microbe that lived and died there billions of years ago. Absolute contamination control. This is the final critical piece of the puzzle. When you're looking for faint ancient traces of life, you must be 100% certain that the life you found is Martian life, and not a stray microbe you accidentally brought with you from Earth. No matter how well we clean a rover, we can never perfectly sterilize a 1-ton robot. The risk of forward contamination is always there, and when the samples are analyzed on Mars, there is a risk of cross-contamination between different samples. A sample return mission is designed to solve this. The Perseverance rover is already sealing its samples in pristine, airtight titanium tubes. When these samples are brought back to Earth, they will not be sent to a normal university lab. They will be opened inside a specially built BSL-4 Biosafety Level 4 facility. This is the same level of containment used for the most dangerous pathogens on Earth, but the purpose will be reversed. The seals are not just to protect us from Mars, but to protect the Mars sample from us. In this ultra-clean environment, scientists can ensure that every molecule they detect, every isotope ratio they measure, and every structure they see is truly authentically Martian. The dazzling complexity of the mission. Because this goal is so important, it is also the most complex and ambitious robotic mission ever designed. It is not one mission, but a cosmic relay race involving multiple spacecraft and the first ever launch from another planet. It begins with the Perseverance rover, which acts as the geologist, identifying the best rocks and sealing them in the sample tubes. It then carefully places these tubes at a depot on the Martian surface. The race continues when a new spacecraft, the Sample Retrieval Lander, launches from Earth. It must land with pinpoint accuracy near this collection of tubes. From this lander, a small, fast fetch rover would dash out, grab the tubes and race back to the lander. Then the most dramatic step occurs. Aboard the lander is a small, solid-fueled rocket called the Mars Ascent Vehicle MAVI. The tubes will be loaded into a container at its tip. This rocket will then fire, launching from the surface of Mars to become the first ever human-made object sent into orbit from another world. But it is not home yet. a separate third spacecraft, the Earth Return Orbiter, will have already been waiting circling high above Mars. Its job is to find the tiny sample container now orbiting the planet, track it, and perform an incredibly difficult automated rendezvous and capture. Once the container is safely secured, the orbiter fires its own engines and begins the long multi-month voyage back to Earth. As it approaches our home planet, it will not land. Instead, it will simply release the precious cargo, a small re-entry capsule, which will blaze through the atmosphere and land via parachute in a remote designated location, where a recovery team will be waiting to finally bring the pieces of Mars to our labs. We have spent a great deal of time looking at Mars not just as a planet, but as a story of water geology and chemistry. Now we must return to the big philosophical question that hangs over all of space exploration. Where is everybody? This question is the heart of the Fermi paradox. The universe is ancient and vast with trillions of planets. Statistically intelligent life should have arisen thousands, if not millions of times, yet we see no evidence of them. The cosmos is silent. This silence leads to a sobering concept known as the Great Filter. The theory suggests that there is some barrier, some incredibly difficult step between the formation of a habitable planet and the emergence of a civilization capable of colonizing the stars. This filter is so difficult to pass that almost no species ever makes it. The critical question for humanity is where is this filter? Is it in our distant past, or is it lurking in our near future? Our search for life on Mars is not just a biological mission, it is the single best test we have to find the answer. The results from Mars, whatever they may be, will have profound implications for our own destiny. Scenario 1, the filter is ahead of us. Let us imagine a future where a rover, drilling deep beneath the Martian surface, perhaps in an ancient river delta or a subsurface aquifer, finds life. It wouldn't be complex animals, but simple single-celled organisms, Martian bacteria. And crucially, let's imagine that when we analyze this life, we find it is biologically independent. Its internal chemistry, its method of storing information, its version of DNA is fundamentally different from ours. This discovery would mean that life started from non-living chemicals, a process called a biogenesis, twice all by itself in just one small solar system. If life can start twice just in our backyard, the implications are staggering. It would mean that life itself is not the filter. It must be common. The universe must be teeming with simple life, a cosmic ocean of bacteria on countless worlds. But if that is true, why is the galaxy silent? This scenario leads to a terrifying conclusion: the Great Filter must be ahead of us. If starting life is easy, then the barrier must lie somewhere between simple bacteria and a galaxy-spanning civilization. This would mean that the hardest part is not starting. The hardest part is surviving. What could this future filter be? There are several candidates. Perhaps the filter is the jump from simple cells like bacteria called prokaryotes to complex cells like our own called eukaryotes. This leap took over 1 billion years on Earth and seems to have happened only once. It was a freak accident where one cell absorbed another, leading to the mitochondria that power all complex life. Maybe this step is so rare that almost no planet ever achieves it. Or perhaps the filter is the development of complex multicellular organisms, or the jump to true intelligence and tool use. But the most chilling possibility is that the filter is self-destruction. Perhaps any species that becomes intelligent enough to develop advanced technology like nuclear weapons, uncontrolled artificial intelligence, or planet-altering industrial processes inevitably uses that technology to destroy itself. In this view, the silence of the galaxy is the silence of a graveyard filled with civilizations that reached our stage of development and failed to pass the test. If we find independent life on Mars, it would be the most exciting scientific discovery ever made, but it would also be the single worst piece of news in human history, as it would strongly imply that we are approaching the main filter, and our chances of survival are very, very slim. Scenario 2. The filter is behind us. Now, let's imagine the opposite. We search Mars for decades. We send advanced drilling missions, sophisticated labs, and eventually human explorers. We scan every ancient lake bed, test every volcanic vent, and analyze every drop of subsurface water. And we find nothing. Not a single living cell, not a single fossil, not even a complex organic molecule that hints at a shadow biology. We find only sterile, lifeless chemistry. This result would be a deep disappointment for biologists, but for humanity, it would be the greatest news we could ever receive. If Mars, a planet that once had all the right ingredients for life, liquid water, organic compounds and energy sources, remained sterile for 4 billion years, it suggests that the origin of life is not easy at all. It suggests that the leap from non-living chemicals to the very first self-copying cell is the most improbable event imaginable. This would mean that the Great Filter is behind us. We passed it. The filter was a biogenesis itself. The jump from a soup of amino acids to a structure with metabolism and heredity like RNA or DNA is the single greatest barrier in the universe. It's so mathematically unlikely that it may have only happened once in this entire galaxy. This would mean we are, if not totally alone, then certainly the first and perhaps the only intelligent species to ever exist. The silence of the universe is not a graveyard, it's an empty cradle. It confirms that life on Earth is not a common chemical reaction, but a precious singular miracle. If Mars is sterile, it means the cosmos is ours. It means there are no advanced alien empires to fear, but also no one to save us from ourselves. The future of intelligent life in the galaxy rests entirely on our shoulders, the complication panspermia. There is a third complicating possibility. What if we find life on Mars, but when we analyse its genetic code we find it uses the exact same DNA system as we do? What if it is essentially our distant cousin? This would be evidence for a concept called panspermia. This is the idea that life did not start independently on both planets, but rather was seeded from one to the other. We know for a fact that Mars and Earth have been trading rocks for billions of years. When a giant asteroid strikes a planet, it can blast pieces of that planet's crust into space with so much force that they escape orbit. These rocks, now meteorites, can drift through the solar system for millions of years before landing on another planet. We have found dozens of Martian meteorites here on Earth. It's entirely plausible that ancient hardy microbes could survive inside one of these rocks shielded from radiation and make the journey from one world to the next. If life started on Mars first, when it was warmer and wetter, and then seeded Earth, it would mean we are all in fact Martians. Or if life started on Earth first, our bacteria may have contaminated Mars billions of years ago. While this would be a fascinating discovery, it unfortunately tells us nothing about the Great Filter. If Earth life and Mars life are related, it means it still only happened one time. We are just two copies of a single data point. We are put back at square one with no way to know if that single origin was a rare cosmic miracle. Filter is behind us, or a common chemical event of filter is here. This is why the search on Mars is so specific. We are not just looking for life, we are looking for truly alien life as second genesis. Only that discovery, or the absolute confirmation of sterility, can help us understand our own place in the silent waiting universe. Our focus on Mars is intense and necessary, but it is crucial to understand that Mars is not the final destination in our search for life. It is the first most accessible step outside our own cradle. The lessons we learn from its cold, dusty plains and ancient dry riverbeds are not just about Mars. They are the foundation for understanding the entire universe. Every discovery, every frustration, and every new question Mars presents helps us calibrate our search for life elsewhere. Stepping back to see this cosmic context reframes the entire endeavour. We are not just looking for Martians, we are learning how to look for any life anywhere. The most profound shift in perspective comes from the discovery of planets orbiting other stars. Not long ago, we only knew of the planets in our own solar system. Today, thanks to powerful telescopes and clever detection methods, we have confirmed the existence of thousands of these distant worlds, and we know from statistical projections that there are billions more in our Milky Way galaxy alone. Many of these are super-Earths, rocky worlds larger than our own, and a significant number are located in the habitable zone of their star. This is the region nicknamed the Goldilocks zone, where conditions are not too hot and not too cold, allowing for liquid water to potentially exist on the planet's surface. This is where the Mars wager becomes so critical. Mars is, by modern standards, a terrible place for life. It is a borderline case. Its atmosphere is thin, offering little protection from harsh solar and cosmic radiation. Its water is frozen solid or long gone. It is a cold, seemingly sterile desert. And yet the evidence is overwhelming that Mars was habitable. It had lakes, rivers, and a thicker atmosphere. We are searching for the fossilized remains of tiny, simple organisms that might have emerged during that brief window of opportunity. Now consider the implications. If a planet as difficult and marginal as Mars came so close to hosting life, or perhaps even succeeded, if only for a short time, what does that mean for the billions of better planets? What about the worlds that are more Earth-like, with stable magnetic fields, thick atmospheres, and vast surface oceans that have remained stable for billions of years? If Mars is the low bar, representing a near miss, then the statistical probability for life on these more ideal Goldilocks planets must be significantly higher. The near success of Mars provides us with a powerful optimistic baseline for the chances of life emerging elsewhere. It suggests that the universe is not sterile, but is instead primed for biology whenever the ingredients are right. While exoplanets expand our search across the stars, Mars has also taught us to look closer to home in places we once dismissed. Our solar system's habitable zone was once thought to be a very narrow band where Earth resides, but the exploration of our own outer solar system has revealed a new paradigm-shifting possibility: icy moons. Specifically, 2 moons have captured the scientific imagination: Jupiter's moon Europa and Saturn's moon Enceladus. These are not rocky worlds like Mars, they are ice worlds. On the surface, they are among the coldest, most lifeless places imaginable, blasted by the intense radiation fields of their giant gas planets. But beneath those thick crusts of ice, perhaps miles thick, lie the single most promising environments for life in our solar system: vast global oceans of blue, liquid, or salt water. These moons possess the 3 ingredients essential for life as we know it, solving the very problems that doomed Mars. First, they have liquid water, and perhaps more of it than all of Earth's oceans combined. Second, unlike Mars, they are protected. The thick ice shell acts as a shield, completely blocking the deadly surface radiation and providing a stable, calm environment for chemistry to unfold over eons. Third, and perhaps most importantly, they have a source of energy. This is not sunlight, it is energy from within. The immense gravity of Jupiter and Saturn constantly pulls and squeezes these moons, a process called tidal heating. This stretching friction heats the moon's rocky cores, and this heat likely creates hydrothermal vents on the ocean floor. We see evidence of this on Enceladus, which actively sprays geysers of its ocean water into space. These vents would spew heat and minerals into the water, creating what scientists call redox energy, or a chemical imbalance. On Earth, similar deep-sea vents which receive no sunlight are swarming with bacteria and complex life that eat this exact type of chemical energy. Europa and Enceladus are, in essence, giant protected energy-rich petri dishes that may have been cooking for billions of years. This brings us back to Mars as our essential model. We cannot currently land on Europa or an exoplanet. We must learn to find life from a distance. Mars is our training ground, our laboratory for learning how to read the signs of life, or biosignatures. When we examine the atmosphere of an exoplanet 50 light-years away, we get only a few faint pixels of data. We might see the signature of oxygen or methane or carbon dioxide. But what does that mean? Oxygen can be produced by non-living geological processes. Methane, which is a strong sign of life on Earth, can also be produced by the simple interaction of water and certain types of rock, a process we suspect may be happening on Mars right now. Mars is teaching us how to tell the difference. By studying a world that is definitively geological and possibly formally biological, we learn to read the subtle clues. We learn to identify false positives. Our rovers on Mars are not just looking for life, they are building the dictionary we will need to interpret the faint whispers from distant worlds. By understanding how Mars failed to sustain life, or how its life died out, we gain the critical wisdom needed to one day look at a faint blue dot orbiting another star and say with confidence that it is not just habitable but inhabited. We stand at a remarkable moment in history, perched on the edge of a discovery that could redefine our place in the cosmos. The journey to Mars, and specifically to Jezero crater, has not been a simple search. It has been an exercise in managing a profound human tension. On one side, we have the thrilling, almost desperate hope to find that we are not alone. On the other, we have the cold, necessary caution of science. This is the great balance, the excitement of what could be, versus the rigorous skeptical demand for what is. We have sent our robotic proxies to a world billions of miles away, and they are sending back whispers of a past that looks tantalizingly familiar. But in science, a whisper is not an answer. The single greatest fear for any scientist in this field is the false positive. Announcing the discovery of extraterrestrial life only to retract it later would be a setback of monumental proportions, would damage public trust and poison the well for future research. This is why the burden of proof is set so incredibly high. The universe, we have learned, is full of traps for the hopeful. The first trap is geology itself. Mars is a planet of wind, water and minerals, and these non-living processes are brilliant mimics. Simple chemistry can create complex structures. Minerals precipitating out of water can grow into branching rounded shapes that look identical to microbial colonies. iron, and other elements can form tiny spheres that at first glance look just like fossilized cells. Geology can also create complex carbon-based molecules known as organic molecules without any help from life. Finding these molecules, the building blocks of life, is exciting, but it is not by itself proof of life. We must first prove that a non-living chemical reaction could not have made them. The second and perhaps more insidious trap is contamination. We are creatures of Earth, a planet that is absolutely teeming with life. Life is in the air we breathe on our skin and inside our bodies. When we build a rover, we do so in clean rooms, where the air is filtered and technicians wear full-body suits. We bake the spacecraft components at extreme temperatures to sterilize them. But life is stubborn. We cannot be 100% certain that a few stray microbes or even fragments of their DNA did not hitch a ride on the Perseverance rover. If we find a signal in a Martian rock, we must first prove beyond all shadow of a doubt that we did not bring it with us from home. This is why the rover carries witness tubes, which are special blank samples. They sit inside the rover and collect any Earth-based contaminants that may be present, so that when the samples are returned, scientists can compare them and subtract Earth's signal from Mars's. This is why the skepticism is so deep. Any single clue on its own would be dismissed. If we only found strange shapes, scientists would blame geology. If we only found organic molecules, they would suspect a biotic chemistry or contamination. But this is not what we have found. The reason Jezero Crater has become the focus of the world's attention is not because of one clue, but because of the convergent package. This is the core of the new evidence. It's the difference between finding a single lonely footprint in the desert and finding a footprint, a tool, and the warm embers of a campfire, all in the same place. The case for Jezero is built on layers of evidence that all point in the same direction. First, we have the context. Perseverance is exploring an ancient river delta, a place where billions of years ago a river flowed into a deep lake. This is precisely the kind of environment where on Earth life would have thrived, and more importantly where its remains would be preserved in the fine-grained mud. Second, we have the minerals. The rover has found clays and sulfates, minerals that form in the presence of liquid water. This confirms the delta was not a brief violent flood, but a stable, long-lasting body of water, a truly habitable environment. Third, we have the organics. In this perfect life-friendly environment, we have found a variety of complex organic molecules. These are the raw materials for life, the very stuff from which cells are made. Finally, we have the structures. In these same rocks, we see textures and fine-scale layers that are consistent with what microbial mats large colonies of bacteria would leave behind. None of these things in isolation would be enough, but finding them all together in the same rock in the perfect location creates a powerful, compelling story. It dramatically lowers the chances that geology is fooling us. This convergence is what makes the samples Perseverance has collected the most valuable objects on Mars. And yet for now, we are met with silence. The rover has drilled its cores, sealed them in tubes, and left them on the Martian surface. As powerful as the rover is, it is a field geologist. It can identify interesting rocks, but it does not have the power to make a definitive discovery. The final verdict cannot be decided on Mars. It must wait. It must wait for a future complex mission called Mars Sample Return, which will send a new spacecraft to land on Mars, pick up those tubes, launch them back into orbit, and finally bring them home to Earth. Only then can we use the full power of our planet's most advanced laboratories to analyze them molecule by molecule, atom by atom. This is the hard truth of science. It does not hurry. It is a slow, methodical, and often frustrating process of eliminating doubt. The burden of proof is heavy as it should be. The answer, whatever it is, will change our world forever. If the answer is no, if we find that this perfect Martian cradle with water and organics and time remains sterile, it would tell us that the spark of life is an almost impossible miracle and that our small blue world is more precious than we can imagine. And if the answer is yes, if we find the undeniable chemical or structural fossil of a simple alien life form, it will mean that life is not a miracle at all, but a natural, perhaps inevitable consequence of geology. It would mean the universe is alive and that we are for the first time in our history not alone. Until that day, we must embrace the silence. We have asked the question. The evidence has been collected. Now we listen, we test, we remain skeptical, and we wait.